YouTube, no canal do CBC, no YouTube.
Só colocar aí CBC.
Já aparece.
Pointer. Okay, so let's begin. So, good afternoon, everyone. So, welcome to our afternoon session of the 6th International Conference on Finite Fields and Applications. So, we have 5 talks this afternoon. So, these 5 talks and 20 minutes each one. And the first speaker is Ankit Yadav. So, the title of this talk is ACD, Acyclic Codes over Mixed Alphabet Z2 Arcade. So, thanks.
So, hello everyone. My name is Ankit Yadav and I am a PhD student at IIT Delhi, India, under the supervision of Professor Ritwani Sharma. So, first of all, I would like to thank the organizers for giving me this opportunity to present my work. So, the title of my presentation is ACD and Cyclic Codes for Mixed Alphabet Z2 Arcade. And this is a joint work with Vidyasagar and Ritwani Sharma. So this is the outline of my presentation. So we start with introduction. So throughout this talk, Z2 denotes the ring of integers modulo 2, and Fq is the finite field of order Q, where Q is a prime power, and a linear code C of length n and dimension k is a k-dimensional subspace of the vector space Fqn, and it is denoted by nk. And the Hamming weight of an element x is the number of non-zero positions in x, and the minimum distance or minimum weight denoted by d of c of a linear code is the minimum of weight of all non-zero code words of C. So if we have a linear code nk, and if d is its distance, then we say it nkd linear code. So if we have a linear code C and a matrix G is said to be generator matrix if its rows form a basis for C. That means they are linearly independent and they are spanning set for C. So then we define the Euclidean inner product. So let V and W be two elements of the vector space Fqn. Then the Euclidean inner product of V and W is V1 W1 plus V2 W2 and so on Vn Wn. And for any non-empty subset W of Fqn, the Euclidean dual is denoted by W per, and it is the collection of all those elements of Fqn whose inner product with every element of W is 0. So then we have the definition of LCD code. So a linear code C is said to be linear complementary dual code if C intersects its dual trivially. And a linear code C is said to be self-orthogonal if C is contained into C per. So LCD codes are widely used in data storage, communication systems, and cryptography. Carlet and Gilly in 2016 showed the application of LCD codes to prevent the side channel attacks and fault injection attacks. So LCD codes were first introduced by Massey in 1964, and later in 1992 he gave a characterization for LCD codes over finite fields. So if C is a linear code over Fq and G is generator matrix, then C is LCD if and only if G star G transpose is invertible. And then Liu and Liu in 2015 extended that result to chain rings. So if C is a free code over the chain ring R and G be its generator matrix in standard form, then C is LCD if and only if G star J transpose is invertible. Also later, Ben Balkashan and others studied the ACD codes, which we will define later, over the mixed alphabet Z2 cross Z4. And Sagar and Sharma extended this work to Z2 cross Z2U over U4. So motivated by this study, we aim to study the ACD codes over the alphabet Z2 cross Z2U over UK, where K is any positive integer greater than equal to 2. So over the time, LCD codes were first studied over finite fields, then they were studied over finite rings, and then they were generalized to ACD codes over the mixed alphabet. So then we have the preliminaries. So throughout this talk, Rk is the quotient ring Z2y over y raised to k, where k is greater than equal to 2. And the unit group of Rk is denoted by Rk star, and it is the collection of these type of elements. Any element A in Rk can be written as A equal to A naught plus A1U and so on, AK minus 1, UK minus 1, where all these A is belonging to Z2 and U is the coset of Y. So we can see that this Rk is a chain ring and also a local ring with the unique maximal ideal M, which is generated by U. So then we define a map theta from Rk to Z2, where any element A naught plus A1U and so on, AK minus 1, UK minus 1 is mapped to A naught. And we can clearly see that this is a surjective map. So let alpha and beta be two natural numbers, and then this set the Z2 alpha cross Rk beta, which contains these type of tuples. So this is an abelian group with respect to the component wise addition. And also, if we define a scalar multiplication, that if we take any element R from Rk and we define a scalar multiplication like this, where eta is the map we have defined earlier. So then this set is an Rk module. So we denote this ring Z2 cross Rk by Z2 Rk, and this is a non-chain ring. Then we have the definition of additive codes. So any Rk submodule of Z2 alpha cross Rk beta is called as Z2 Rk additive code of block length alpha beta. And if S is any subset of Rkn, then this S is said to be Rk linearly independent if we take any elements, M elements x1 up to xm in S and lambda is in Rk such that lambda 1 x1 plus lambda 2 x1 and so on lambda xn equal to 0, then all these lambda must be equal to 0. So then we define an inner product on Z2 alpha cross Rk beta. So we take two elements x and y from Z2 alpha cross Rk beta and we define the inner product like this. So inner product of x and y is UK minus 1, the Euclidean inner product of V and W, and the dot product of V prime and W prime. So then we define the ACD codes. So A Z2RK additive code, C, this is said to be additive complementary dual code or ACD code if C intersects its dual trivially, like we see in the LCD codes. So, and the inner product is like in this equation we have written. So, if we have a Z2RK identity code C, then the projection on first alpha coordinates is denoted by C alpha, and this is a binary linear code. And the projection on last beta coordinates is C beta, which is a linear code, additive code over RK. So then we have some basic results. So if A is a square matrix of size n cross n over Rk, where A equal to A naught plus U tilde, then A is then determinant of A equal to determinant of A naught plus U gamma, where gamma is some element in Rk. And then we have a corollary. So if A is n cross n matrix over Rk, then A is invertible over Rk if and only if A naught is invertible over Z2. And then we have a theorem. So if A is n cross n square matrix over Rk, then A is non-invertible over Rk if and only if there exists a non-zero element x such that Ax transpose equal to 0. So we will use these results later on. So now we move on to the main results. So suppose we have matrix G equal to G alpha and G beta, where the entries of G alpha are from Z2 and the entries of G beta are from Rk, and we define as the matrix multiplication G star G transpose like this. So in this matrix multiplication, we are taking the inner product which we have defined earlier, the inner product of every row with every column. So in this way, this matrix multiplication is defined. So then we have a theorem. So if C is a Z2RK additive code of block length alpha beta and G be its generated matrix, then C is ACD code if G star G transpose is invertible over RK. So the converse of this theorem is not true in general. So we can see an example. So if we consider this G to be our generator matrix, then the code obtained C is ACD code, but we can see that G star G transpose have determinant 0 over Rk. So G star G transpose is non-invertible. So converse is not true. So now we will see that converse of theorem 2 will be true if we take an additional hypothesis. So if C is a Z2RK additive code of block length alpha beta and G be its generator matrix, and the rows of G beta are RK linearly independent, then C is ACD code if and only if G star G transpose is invertible. So we will see a quick proof. So first we assume that C is an ACD code over Z2RK and Xj is the Jth row of matrix G. And first we assume that G star G transpose is non-invertible. Then there exists an element V such that non-zero element V such that G star G transpose times V transpose equal to 0. And if we fix X equal to V times G, then clearly this X element belonging to our code C, and also the inner product of X with every row of G is 0. So this is also belongs to C per. So X belonging to C intersection C per. So this is a contradiction. So our G star G transpose is invertible. So conversely, if we take an element X from C intersection C per, so since X is belonging to C, so there are these elements lambda 1 up to lambda L such that X equal to lambda 1 X1 plus and so on lambda L XL, and also C belonging to C per. So the inner product of X with every row of G is 0. So in this way, G star G transpose times this lambda 1 up to lambda L equal to 0. But our G star G transpose is invertible, so all these lambda i's must be equal to 0. So if all these lambda is equal to 0, then this X, this will be equal to 0. So this means C intersection C per is 0. So this is an ACD code. So next we have some corollaries. So if G be a generator matrix such that all the diagonal entries of G star G transpose are units and all other entries are either 0 or UK minus 1, then the code generated is an ACD code. And if take the generator matrix like this, G alpha and Xi IL, where Xi is some unit and I is the identity matrix, then the code generator is also an ACD code. So now we will see some situations when both C alpha and C beta are LCD code, but still C is not an LCD code. So if we see in this example, if we see the C alpha is nothing but Z to 2. So it is LCD code, and similarly C beta is also LCD, but the C instruction skipper contains this element, so this is not an ACD code. And next we have, if neither C alpha nor C beta are LCD code, but still C can be an ACD code, so we have an example. So next, with the help of Z2RK additive code, we obtain the binary LCD codes. So if C is a Z2RK additive code of block length alpha beta and Z is generator matrix, such that the projection C alpha is binary self orthogonal code, and the rows of Z beta are RK linearly independent. And if we take any injective gray map on RK such that phi k C beta is LCD, and if we extend this map phi k to phi like this, then this is also a binary LCD codes. So this works for any injective linear gray map. So in particular, we give a gray map. So first, there is already in the literature a gray map from R2 to Z22 as A plus UB is mapped to B comma A plus B. Now we recursively extend this map to R2 raised to power k, and then this map phi 2 raised to k can be extended to this map phi. And with the help of this map phi and the theorem which we have seen earlier, we obtain some codes with good parameters, and all of them are LCD. So now we will see the notion of cyclic codes in Z2RK. So a code C is a Z2RK additive code C of block length alpha beta is said to be cyclic if C is closed under cyclic shift. That is means cyclic shift in each block, and we denote this product in Z2X by x raised to alpha minus 1 times RKX x raised to beta minus 1 by RK alpha beta, and there is a one-to-one correspondence between this Z2 alpha and RK beta and RK alpha beta, which is given by like this. So this RK alpha beta, this is an RKX submodule, RKX module with respect to this scalar multiplication, where Bx is any element in RKX and Vx and V prime x are elements of RK beta, and eta Bx is the eta map applied to every coefficient of Bx. The eta map we have seen earlier. So next we define the next we have a proposition. So if C is a Z2 RK additive code of block length alpha beta, then C is cyclic if and only if it is an RKX submodule of RK alpha beta. Bethwal and Biswas find the generator polynomials of any cyclic codes over Z2 RK. So these are the generators they found, and with the help of these generators, we aim to find the generators of its dual. So if C is a Z2RK cyclic code, then its dual is also cyclic. It is very easy to see, and then we define the reciprocal polynomial Hx, where if Hx equal to summation I from 0 to t, such that Ht is non-zero, then the reciprocal polynomial is H star x, which is defined like this. So with the help of then, if we consider any Z2RK cyclic code C, then that is the relation between the generators of the dual and the generators of C. So this is the summary. So in this work, mainly we have established a necessary and sufficient condition for Z2RK additive code to be ACD codes, and with the help of gray map, we have found some LCD codes with good parameters. And also we have found the generator polynomials of the dual of cyclic codes, because in earlier literature some authors have found the quantum codes, some new quantum codes with the help of Z2 cross Z2U over U4 and using the cyclic codes, and they are generators. So one can also find the quantum codes with the help of Z2RK. So the results are based on our published article, and these are my references. Thank you for your attention.
Thank you. So are there any questions?
Is there any codes
after gray map that we cannot find using the finite fields. Is there any new code? Can you show us that there is a code you cannot obtain using the additive group of finite fields? Like said, like when we found, like we didn't found any new code, but we only found the codes which are already optimal. So, but in quantum code, we have seen like some authors have found the quantum codes which are new, like the parameters were new. So, like we have, I have seen some papers, but like due to lack of some resources, like we didn't find any new codes. We did only find the optimal codes, which are LCD codes.
Other questions? So I have one. So you mentioned optimal codes, and so it's regarding to which bound. So
These are distance optimal.
okay.
These are distance optimal codes.
Okay. Other questions? So we have a few minutes, 3 minutes, okay? Thank you. Tem mais tempo. Tá bom, depois terminou. Sorry, so we have more minutes, so that's 7 minutes. Teve duas pessoas, né? Um já saiu. Não estou vendo aqui, acho que ele foi no banheiro. Acho que ele foi no banheiro. Acho que ele voltar na quem que é o próximo? Eu vou rapidinho, já volto.
Adam burada değil ama spirit olarak burada. Like different. No, yeah, I'm going there for sure. Yeah, I mean, it's actually partially why. So close to the shopping mall. And shopping malls. At least something. Yeah, there's
So, our second speaker is Virtual Baracas. So, the title of this talk is PR Schemes for ND secret and the constant codes and their monomial equivalence. Please.
Hello everyone, I am Gülcecan Ferkaş from Middle East University, it's Technical University from Turkey. And this is the joint work with Marcus Gressel, Ferro Osterberg, and Scott Austria. And my title is PRI schemes from ND cyclic and ND concentric codes and their monomial equivalence. This is my overview. I'm going to start with private information retrieval, which is PRI. Preliminaries and PRI schemes from ND cyclic codes. And after that, I will explain the monomial equivalence of ND cyclic and ND constant cyclic codes, and I will finish my presentation. So, what is PRI? PRI allows data to be retrieved from a database without revealing the identity of the data items. And there is important two terms, PRI rate and collision number. PRI rate is the ratio of the information gained to the information downloaded. And the collision number is, it's a common for PRI schemes to assume that servers may collude, meaning they share information about their interaction with the user. And the most common collision model is decollision. In 2018, Trajan Holland et al. They showed the PRI scheme, which is called C private information retrieval scheme. And in this scheme, we have two binary codes. One of them is C, which is a storage code, and the other one is retrieval code. In this scheme, we have N servers and files, and the user wants to download W files. F is an arbitrary finite field. This is the most basic explanation of the scheme. Here we have arbitrary files as x to the I, and the stored data in the servers are y to the I, which is calculated as multiplying arbitrary files by generated matrix of the storage code C. Then for every x to the I, there exists a code word e to the I from D, the retrieved code. And let's see from this set, then we add this e to d to the omega from here, you can see. And this n times n matrix, the columns of this matrix gives us queries, qj to the w. And this qj to the w's, these queries, sent to the j server, every j server. Then the server sends these r to the w responses as in this vector form. Then the code retrieved by multiplying some parity check matrix of C should product D. After that, the data is retrieved. And in their work, they prove that the PRI rate for C and D just linear codes, the PRI rate is this, which protects again the D sub D do minus 1 collision. This is T collision means. And then they showed that when C and C should product D is transitive, they improve this rate into this, which protects again the same collision number. So, and in 2022, Bodur et al. Used cyclic codes. They are also transitive codes, and they obtain better PRI rates. So, in our work, we use anti-cyclic codes. We show that they are transitive, and we obtain better PRI rates according to their results. To show that, first I'm going to show that anti-cyclic codes are transitive. These are the preliminaries. This is a linear code is cyclic when this code is in C, then this code, one cyclic shift version should be inside the C again. R is a disquotient string, G of X a generated polynomial, and here defining sets and generating sets are rely on the zeros of the cyclic code C, and then take the exponents of the primitive roots. So if we know the defining set of the cyclic code C, then we also know the defining set of C-do here. And we need to see the cyclic codes as an evaluation code, like here, to show that true product of two cyclic codes is again cyclic code, as Cascado does here. So we can read as two cyclic codes, true product of two cyclic codes as an evaluation code on this defining set. So therefore, the true product of two cyclic codes is again cyclic. Then this is the anti-cyclic code definition. It's this many lengths over FQ and defined to an ideal in this set, this quotient ring. And here we have shown that the transitivity of the cyclic code, if we want to carry the element from I1 position to I2, we have two options here. We must do I2 times I2 minus I1 cyclic shift operation, or n plus I2 minus I1 times cyclic shift operation. Then the cyclic codes are transitive, so we can generalize this idea for 2D cyclic codes also. Here we have two cyclic shift operation, row shift and column shift. and we want to go from this position to I2, J2 position. And here we have 4 options. One of them is this one, and these are the other 2. And we can say that 2D cyclic codes are also transitive codes. And for the finally, we can generalize this idea into ND cyclic code setup with n variables. Then we can say that ND cyclic codes are also transitive codes. Therefore, we can use these ones for KRI schemes also. Here in okay. So what Cascudo did for the cyclic codes, this idea improved by Günner Özbudak in 2008 for ND cyclic code setup, and we can see ND cyclic codes as an evaluation codes also. So by using this property, we can prove that true product of ND cyclic codes is again ND cyclic codes. And here we have n-varied polynomials. The bold notation represents n tuples here. And also we can generalize the result of Cascudo for ND cyclic codes also. By that we can say that ND cyclic true product of ND cyclic codes are again ND cyclic codes. So now our results are in Baudou et al. They proved that the binary cyclic codes of length 63 can achieve 6/63 KRI rates with the collision either 15 or 19. So if you look at the first table, we used 2D cyclic code pairs of length 63. They are strictly 2D cyclic code. They are not isomorphic to cyclic codes here. And if you look at the 15 collision number, we have better PRI rates than 6/63. And for the last one, for 6/63, we have 17 collision number. And if you look at the table 2, when C is a repetition code, we have a better result. And if you look at the last 3 lines, they are strictly better for PRI rate and collision number also. These are our magma results. So to show the monomial equivalence of ND cyclic and ND constant cyclic codes, we have permutation matrix of cyclic shift, this matrix, and also we have the monomial matrix of alpha constant cyclic shift. So we need this M matrix to show the monomial equivalence between cyclic code and alpha constant cyclic code. And for that, we need to solve this equation. And for this, beta should be non-zero, because if beta is 0, then we get alpha is equal to 1. And we don't want that. It's equal to cyclic shift. And this result is also in Biar-Brouwer paper with a different notation. So we need to, for this, we need to satisfy that alpha has to has nth root over Fq. And we call this as beta here. So for satisfy this property, we need to satisfy this equation from the finite field group. So by satisfying this relation, we get this M matrix, which is satisfied with ones. Therefore, alpha constant cyclic codes and cyclic codes are monomial equivalent. And in a polynomial representation, we can say that if g of x is in this form, then we can say that the generator polynomial of alpha constitutive codes can be represented as this way. And since we don't have the same metric set up in two cyclic codes, we only used polynomial representation to generalize this idea. And you can see from here, this is the generator matrix of two cyclic code C, and this is the generator matrix of alpha delta constitutive code, this code. And also, by using these, we can generalize this idea into endocyclic setup. After that, we can say that endocyclic codes and endoconstitutive codes are monomially equivalent. And these are my references. Thank you for listening. Any questions?
So, questions?
Can you explain why it's better to have collision number high?
I'm not sure actually right now. Hocam.
If more servers support you, you probably have protection.
Okay. More questions? So I have one. So do you think your ideas, your construction, you can use the similar ideas for skew codes, for example?
For what?
Skew codes. So you do for n cyclic codes, skew. It's just similar, so you use polynomials in a different way. So.
I'm not sure, but I will check.
Okay.
Thank you.
Okay, let's think again. Twelve minutes.
Yani çünkü şey var, onların şeyi değişiyor.
I think you are right, we didn't stay.
Maybe it's possible, but I don't know how. Maybe the next step. Não sei. Eu tinha visto no começo você tirou o meu. Você tirou. Não, prisão, né?
Çok daha uzunlaştırıyor. O zaman çıktığı zaman da yeni şey geliyorsun.
Yukarıda olabilir.
Na verdade, tem corrigir provas do seguinte. Da graduação de sul, e aí eu deixei aberto devia ter fazer algumas comissões e mandar após explicar como, né? Espera uma semana para fazer, aí ensinar para ele. Isso, acho que era muito ali. Acho que já passei não sei se foi na terça ou na sexta, acho que era na terça, porque a sexta é aquelas coisas. Hoje tinha deixado o ano passado. Vai ser começou em março. Então, vai fazer mais. Mas não, yes. Mas eu fiz uma aula especial para primeira graduação. A tentativa, curva, mais matéria. Mas o mestrado eu consegui fechar pouco. É, mas eu fiz interrogatório também. Eu fiz na BO, VC, acho inteligente, não pode ser isso. Ele falou. Então tá bom, eu pensei que eu estava muito acolado. Eu pensei que ia ser uma atrás da outra, né? Meu carro. Mas acho que mais ou menos 5. Tem 5. Na verdade, eu não reparei lá que tinha 5 minutos. Eu achei que ia ser colado para da manhã ainda. Não, ia ser super rápido, porque ficar sem pergunta também não dá. Posso entrar agora? Até falar se quisesse ficar na minha sala, eu acho que ia dormir. Acreditava. Não, já. Não sei se ele costuma acordar assim, né? Acho que ele acordava assim às 10 horas, 11 horas. Eu passei mal. Dependendo do que vai fazer. Eu fui relaxado, cheguei aqui já 9 horas já. Na verdade, eu toquei essa colinha. So we have 2 minutes. Let's check again. So, okay, let's go to our talk. So now we have a presentation with Kumar Gaga and secret codes with help of cyclotomical polynomials.
Hello everyone, I am Anuj Bhagat. I am doing my PhD in the Department of Mathematics at IIT Delhi, India. And my today's topic for presentation is cyclic codes with the help of cyclotomic polynomials. So let's see some basic introduction, which most of you are already aware of, but I'll be quickly going through a few quick notions. So throughout this talk, Fq denotes the finite field of order Q, and where the characteristic is assumed to be P. A linear code of length n and dimension k over Fq is a k-dimensional subspace of Fqn and usually called an nk code, and Q is clear from the context. And elements of C are called as code words. So for a vector V in Fqn, the humming weight of V is a number of non-zero components in V. So for an nk code C containing at least 2 code words, the humming distance of C is minimum of the distance between x and y, where x and y are from C and x is not equal to y. So if the distance d of an nk code is known, it is often referred to as nkd code. So we have a very nice bound, which is called as a singleton bound, that any linear code with parameters nkd satisfies this inequality, which is d is lesser equals to n minus k plus 1, and any linear code satisfying this bound is termed as maximal distance separable code, or simply an MDS code. So a linear code of length n is called cyclic code if it is closed under cyclic shifts. That is, whenever a0, a1 up to an minus 1 is in C, then all its shifts are also in C. So if I define map phi from Fqn to the quotient ring Fqx quotient by x to the power n minus 1 in the natural way, that is a0, a1 dot 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 goes to a0 plus a1x and so on, then this is an isomorphism of vector spaces over Fq. Okay, and if you identify an element here with an element here in the with the help of this map pi, then we have a very nice characterization for cyclic codes, which is non-empty subset C of Fqn is cyclic if and only if pi c is an ideal of this quotient ring. So this quotient ring is actually a principal ideal ring. So every ideal here is principal. It is generated by some element, and a generator of this ideal will be called as the generator of the cyclic code. So more formally, we have this. So given a non-zero ideal I in Fqx quotient by x to the power n minus 1, there is a unique monic polynomial gx in Fqx of the least degree that divides x to the power n minus 1 and generates I. We call such a polynomial gx the generator polynomial of I. And for a cyclic code C, the generator polynomial of pi c is called as the generator polynomial of C. So once we have the generator polynomial and the length of the cyclic code, we can easily determine its dimension, which is the dimension is given by length minus the degree of the generator polynomial. And yeah, so this is the notion of inner product and the dual of a code. So for two vectors u and v in Fqn, the Euclidean inner product of u and v is defined to be inner product of u comma v is summation j running from 0 to n minus 1 uj vj, and the Euclidean dual, or simply the dual of an nk code C, is defined to be this. That is, all those vectors in Fqn whose inner product with every code word is 0, right? So one thing is important to note here, that inner product of u comma u is 0 may not imply that u is 0. So as a result, C intersection C per may not be just the singleton 0 element. So this motivates the definition of an LCD code. So linear code C is called LCD, or linear code with complementary dual, if C intersection C per is just trivial. So yeah, let's quickly recall something called as the nth roots of unity. So if you look at this polynomial x to the power n minus 1, so if you look at the roots of this polynomial in a splitting field, so all the roots of this polynomial are called as the nth roots of unity over Fq. And if the characteristic, so if n is such that it is co-prime to the characteristic of the field, then all these roots actually forms a cyclic group of order n under multiplication. So basically what we are doing is we are taking the roots of x to the power n minus 1 in the splitting field of x to the power n minus 1, and if n is co-prime to the characteristic of the field, then the nth roots of unity actually forms a cyclic group of order n under multiplication. So a generator of this cyclic group will be called a primitive nth root of unity over Fq. So because it is a cyclic group of order n, it has phi n or phi n generators, where phi is the Euler's quotient function. So we construct a polynomial whose roots are all the primitive nth roots of unity. So if I know that zeta is one primitive root of unity, then all other primitive roots are zeta power s, where s is co-prime to n. So this polynomial is termed as the nth cyclotomic polynomial over Fq. So this has very nice properties that all its coefficients actually lie in the base field Fq. Okay, and it is a divisor of x to the power n minus 1. Okay, so I'll come back to this later. I'll just simply say this. Okay, so if I talk about the cyclotomic polynomial Qnx, so it is a divisor of x to the power n minus 1. So it is very natural to ask, like, what happens if I generate a cyclic code with the polynomial Qnx? So I looked into the literature, but I could not get much information. So the previous work on generic construction of QRA cyclic codes considered certain multiples of the cyclotomic polynomials using this reference. And but if you think if D is a divisor of n, then QDX is a divisor of x to the power n minus 1 in FQX. So therefore, it is very natural to ask the parameter of the cyclic code generated by QNX. And also, I have also considered another family of codes generated by QNX times the polynomial Q1x. So this was the first fundamental question which can be asked. And I'll talk about this a bit later. So let's see the main results. So if n is a natural number such that it is co-prime to the characteristic of the field, then the cyclic code Cn, which is generated by Qnx, has parameters. So the length is n, the dimension is n minus phi n, and the distance is exactly equal to LPFn. What is the meaning of LPFn? It is the least prime factor of n. So the length is clear because Qnx is a divisor of x to the power n minus 1, and in fact the order of Qnx is exactly n. So it cannot divide x to the power d minus 1 where d is strictly less than n. So length is clear, and dimension is also very clear because degree of degree of Qn is phi n. So the dimension will be n minus phi n. So the only interesting part is the distance. So to prove that the distance is exactly LPFn, I constructed a code word whose weight was exactly the least prime factor of n, and the other inequality was achieved using the BCH bound. So similarly, we have for a composite number n, which is co-prime to the base field, the cyclic code Cn, 1 generated by Qnx times Q1x has the following parameters: n, the dimension is n minus phi n minus 1, and the distance gets doubled, so it's 2 times the LPF of n. So this characterizes all the cyclic codes generated by Qnx and Qnx times Q1x, and in fact it is independent on the base field. The only n depends on the Q, but whereas the parameters of Cn are independent of the base field Q. Okay, so you might be thinking that why have I considered composite number here, and what about the prime number? So if n is prime, then Cn1 is the zero code, since Qnx times Q1x becomes x to the power n minus 1 in this case. Okay, so one may ask about what happens to the duals of these codes. So also it's very easy to prove both of these codes, these families of codes, are LCD codes. Okay, it is a very straightforward argument to prove this. So we have a very basic lemma from number theory that the linear combination of reciprocals of a finite number of distinct primes with coefficient plus or minus 1 is never an integer. It is also not very difficult to prove. So with the help of this, we have characterized something about the dual of the code Cn. So again, as usual, that suppose n is a positive integer co-prime to the characteristic of the field, then the dual of Cn per has the following parameters. So the length is obviously clear and the dimension is obviously clear, phi n, but I have proved that the distance cannot exceed 2 to the power omega n. And what is omega n? It is the number of distinct prime divisors of n. So again, it depends on the prime factorization of n. So it will not exceed 2 to the power omega n. So I have a very quick outline of the proof for the same. So basically the idea is to construct a code word whose weight is exactly 2 to the power omega n, and that will indeed prove that the distance cannot exceed 2 to the power omega n. So the length and dimension are clear, and if hx is this polynomial, that it is x to the power n divided by q and x, then we actually show that hx is the parity check polynomial for C, and hence a generator polynomial for C per. And if we assume that this is the prime factorization of n, where p1, p2 and pk are distinct primes, okay, so and if I take this for every I, if I denote ni to be n divided by this pi, and so we have shown that this polynomial x to the power n1 minus 1 up to x to the power nk minus 1 is actually is in Cn per. With some arguments, we have actually proved that this is in Cn per. Now we show that the weight of fx is exactly 2 to the power omega n. So using the previous lemma, we have actually proved that the weight will be exactly equal to 2 to the power omega n, and this completes the proof. The argument is simple, that it will not exceed 2 to the power omega n. Now one may think whether this is achieved or not. So in fact, oh sorry, let me also complete about what about the dual of the code C n n1 per. So the dual of n1 per will also not, the distance of dual of C n comma 1 will also not exceed 2 to the power omega n. The proof is very simple because C n comma 1 is contained inside Cn. So we have this inequality for the distance of the duals, and as a result, because we have proved this one as 2 to the power omega n, so this will also be lesser or equal to 2 to the power omega n. Okay. So this bound is actually much better than what is. So if I use the singleton bound here, the singleton bound here to achieve an upper bound for the distance, then the singleton bound gives us here n minus Pn. So which tends to infinity as k tends to infinity. So the bounds that I have achieved is much better what is given by the corresponding singleton bounds. Okay, so we have actually proved that the distance is exactly 2 to the power omega n when n has at most two distinct prime divisors. So that means we have achieved this equality when n has at most two distinct prime divisors. So the proof, that means in this case the distance will exactly be 4 because n has two divisors p1 and p2, so 2 to the power omega n, which turns out to be 4. But in fact, using the Magma software for n ranging from 1 up to 512 and q ranging from 2 to 19, I could actually check that this distance 2 to the power omega n is always achieved. So this gives the following conjecture, that given any composite number co-prime to the base characteristic of the base field, the dual of Cn comma 1 has parameters or has distance exactly 2 to the power omega n. So I have already proved that it is always lesser or equal to 2 to the power omega n, but I'm not able to prove that it will be exactly equal to 2 to the power omega n. It is still an open problem, hence a conjecture. And similarly, I have conjectured the same thing for Cn comma, the dual of Cn, which is also exactly 2 power omega n. So this will complete, if you can prove both of these conjectures, it will complete all the information about the cyclic code generated by Qnx and Qnx comma Qn1x. However, one of the conjectures will imply the other. So conjecture A actually implies conjecture B, and here's a very simple proof. If n is a prime, then we have already proved conjecture B, and if n is composite, then conjecture A implies conjecture B due to this following inequality. So the only task that remains is to prove conjecture A, and it is still open. Okay. Now this was the characterization of codes generated by QNX. I hope I have some time.
Yes, 5 minutes.
Okay, thank you. So this characterizes the family of cyclic code generated by QNX and QNX times QNX. So just to find some application, so I'll just go back to the motivation section. Yeah, so some information based on something called as LRC codes. So locally recoverable codes or repairable codes. So linear code is said to be, the ith component of C is said to have locality R if Ci in each code word can be recovered by R other components. That is, Ci is a function of Ci1 up to Cir. Okay, and the code is said to have locality R if every component of C has locality at most R. So if we know the locality of a linear code, we denote it by NKD and R. So R denotes the locality, and it is clear from the definition that one desires to have the smallest locality because we want to recover a particular component, a component of a code word by all other components, and we want to use least number of components, and we have some trades off. So this is singleton-like bounds for an LRC, and any LRC achieving this bound is actually termed as distance optimal, and an NKD-R LRC is said to be R optimal if there is no NKDS LRC for all S less than R. So there is a very nice result. We can easily determine the locality of a cyclic code if we know the distance of its dual. So it is simply any cyclic code over Fq with dual distance deeper lesser equals to R plus 1 has locality R. So just to show some application, I could construct, so let's go back to the motivation part again. So if you look at some families of LCD codes which are also LRC, so the previous constructions which for codes which were both LCD and LRCs were not very generic and had a lot of assumptions on the underlying cyclic code. So however, the construction that we gave has no such assumptions on the length or anything else. And okay, so let me come back to the results part again and conclude it. So we could find some families of cyclic LCD LRC codes which are also optimal, R optimal and D optimal. So here are some results which we can find. Like we have some families like this with locality 1 and distance P1, and we have some other families which are obtained. This is just simple application of the previous results, that the families that we gave are actually LCD as well as LRC with the following parameters, and they are optimal in some case. So the following, all the results were based on this following paper. So thank you for your attention.
Are there any questions?
I want to know if you think about availability in this LRC code.
Sorry, couldn't get it.
Availability, when in fact you found some sets with locality. For any point, you have say G sets with R points in each set, and with each set we recover
The missing code, missing component.
Yes,
No,
it's called availability.
No, I haven't worked in that.
Maybe you can see.
Sure.
I couldn't understand the effect of being LCD on the locality. I mean, are they related or
No.
it's just an extra condition?
They're not related by any means. LCD is something else and LRC is also something else. But I could find in the literature that people have worked. Like if you look at this paper on cyclic codes that are LCD codes as well as their LRC. So this was just a simple motivation for me.
But I mean, being LCD comes in the package as all cyclotopic polynomials are self-reciprocal.
Right. True.
So
That is still true.
yeah.
Yeah,
I mean,
they are-
but all the reciprocal divisors of x to the n minus 1 has been studied. That's
Okay.
why maybe you might want to compare your results with them.
Okay, I'll see that. Okay, sure. Yeah.
Yes.
Question just about definition. The APP is the number of the primes factor of
So LPFN.
LP.
Fn.
Yeah.
So it's the least prime factor of n. So the smallest prime dividing n.
Oh, okay.
Any other question? So I have one about the conjecture that mentioned.
Right.
So can you say something about the obstacles? So do for two primes, and you have two primes dividing n.
Right.
So what's the difference?
So for this one, so distance is actually 4. So I have proved this. The proof is very long enough, to be honest, and I have used the brute force. That means I have showed that this code cannot contain a code with weight 1, 2, and 3. So that implies distance will be at least 4. but I cannot use the brute force for, in fact, 3 primes. When n has 3 distinct prime devices, the distance is actually 8 according to the conjecture. So I cannot use the brute force to show that it does not contain any code words with weight less or equals to 7.
Okay.
And with increasing primes, the distance will increase, and hence the brute force process will not follow.
Okay. Thank you. Any other question? So let's think again. The speaker. So now have a coffee break in the same place. Se tiver aqui, tem, deve ter. É, no meu caso, a aula não fechava ali, eu achava de colorido. Gostava de colorido. Tá tudo aqui, pronto. the previous
Right.
So we start our second part of our afternoon section with Samir Suena. The title of his talk is New Quantum Codes from Twisted Group Rings.
Thank you, André, and thank you all the organizers for giving me the opportunity to share my research. And this is a joint work with Professor André Pereira from Universidade Federal Rural do Rio de Janeiro, who is the expert on quantum codes. And I will try to show you how to obtain quantum codes from classical codes. And the first is the definition of a constant cycle code. Everybody knows this definition. Everybody has seen this definition all along the day. We just working first with a finite commutative ring, and linear code over R is just a R submodule of R to the n, and we pick some unity in this ring, lambda, and we say the code is lambda constant cyclic if we apply in every word the cyclic shift and multiply the first coordinate by lambda. It's a new word that belongs to the code. Okay? Just for lambda equals 1, we have every well-known cyclic codes. If lambda equals -1, we have negative cyclic codes, and it's well known these codes can be realized as ideals in factor rings. R, the polynomial rings over R, factored by the ideal generated by x to the n minus lambda. And in this case, when we're working with on cyclic code, these kind of codes also are ideals in group ring. Okay, just taking R, this set, of course, is the set of all linear combinations, elements, the coefficient are in the ring, and G belongs to the group, the cyclic group C. Okay, so cyclic groups can be realized as ideals and factor ring, and ideals in group ring using the cyclic group. Okay. As we know, the constant cyclic codes are generalizations of cyclic codes, and we try to describe this kind of codes using a very nice generalization of group rings. Okay? The Hamming weight of any word here is the number of coordinates different from 0, and the Hamming weight of the code, of course, is the minimum weight of the non-zero words. Okay? So, what is a twisted group ring? We just start with a set G bar, which is a cope of the group G, and we define the multiplication in the basis. We are just taking the elements G bar as a basis of this over the ring R of this new ring, and the multiplication is given by G bar times H bar is just a coefficient here, gamma GH times GH bar. And this element here is called, has to be a unity of the ring R, and this mapping, it's called twisted. And of course, if we take the twisted equals 1 for every H and G, we have exactly the group ring. Okay? In order to be associative, this ring, this condition holds, and these conditions tell us that this mapping gamma is a tuple cycle. Okay? So, in this way, we can describe constant cyclic codes, or lambda constant cyclic, just as an ideals inside the twisted group ring of a commutative ring R and a cyclic group Cn, just given by this mapping. And for cyclic groups, the twisting defined in this way is can cover all tuple cycles in this case. All tuple cycles in this case can be obtained in this way. Okay? For those who knows this mapping, if we forget the bar, we just have exactly the same mapping that realize cyclic codes as ideals in twisted group ring. Okay? When we are just looking to this new ring, we can describe special kinds of codes using the structure of the ring. Okay? First, we can, in this case, we can just replace the powers of G, GK bar. We can replace these elements by G bar to the K, and we have a different basis for this ring. And the only difference is here when we take the G bar to the end. Here we have the lambda or unity element in the ring R times 1. Okay? So it's almost just in case of the group rings. The only difference is the power, the n power of G bar. Okay? And how describe some, as I told you, special kind of codes using this structure? Again, for group rings, we know if we take this mapping and extend this mapping by linearity to the group ring, we have a mapping which is an involution. But here, when we are looking to using twisted group ring, this mapping is not always an involution. We have to put an extra condition on the twisting. The condition is exactly this one. Gamma square has to be 1 for any elements G and H. Okay? It's also we have also these elements G bar are units in the twisted group ring. So you can this mapping is well defined. But we have to put this condition or extra condition to obtain an involution, and this mapping is called classical involution. Okay? Well, this condition seems to be a little bit restrictive, but we are going to see that in our case is just what we need. Okay? We have seen the definition of Euclidean inner product here, and using the twisted group ring, this inner product is just defined as we multiply just coefficient Pointwise?
Component-wise.
Component-wise, the coefficient, and take the sum. This is exactly the Euclidean inner product. And we can define, of course, if we have some twisted group code, we call just a twisted group code any ideal inside the twisted group ring. If we have some twisted group code, or here we can think that code is a lambda constant cyclic. The dual code is just the set of elements of the twisted group ring that is orthogonal to all elements the code C. And what can you say about the dual code? If C is a lambda constant cyclic code, it's dual. It's a lambda minus 1 constant cyclic code. Okay? So basically we are working on different algebraic structure. Okay? It's a very well-known result. But we are working with LCD codes. LCD codes, we have seen today this definition, are those codes that intersect its dual trivially. Okay? We have a very nice proposition. If lambda minus 1 is different from lambda, any lambda constant cyclic over commutative, a finite commutative ring, is LCD. Okay? So in order to obtain, in fact, only the codes are trivial ones. So in fact, in order to obtain very different nice codes or good codes, we have to put the condition lambda squared equals to 1. Okay? So in our case, if we look the twisting defined by equals lambda or 1, this condition tells us lambda squared has to be 1. Okay? So we are exactly with this condition here. Okay? And we can prove for LCD codes, or if you have LCD codes or lambda constant cyclic LCD codes, this code has to be generated as ideal by an idempotent element, and this idempotent has to be fixed by the involution. Okay? So we are now we can use this result. Again, this property has to be considered. So we have the classical involution, and we can give a very nice characterization of the LCD codes over using twisted group rings structure. Okay? How to construct quantum codes from classical codes? I should thank Claude for the very nice talk in quantum codes. After his talk, I just realized maybe I have nothing to say, but I believe, I hope I have something to share. Quantum code is just a subspace of this Hilbert space, Pn dimensional Hilbert space, and we denote this quantum codes using this notation. And we have one tool here, is just the entanglement assistant quantum error correction codes, and we denote this kind of construction by or this kind of codes obtained by this construction by n, k, d, c, and c is just the entanglement maximal states. And when our classical code is LCD codes, we can obtain exactly an entanglement assistant code where C is just n minus k, and this kind of codes, it's called a maximal entanglement assistant codes. Okay? So, some examples of very nice codes. First, we are considering F2. In this case, we do not have codes different from cyclic codes because this element has to be a unit, and our code has, our field has only two elements. In this case, we are working on group rings, and we can consider this element here. Cn is the cyclic group generated with 19 elements. We can take this element here. It's very easy to check this element is idempotent, and when we apply the classical evolution, we have the same, we obtain the same element. And in this case, the code generated by this idempotent, it's a MDS code, a maximum distance separable. This code achieves the singleton bound, and this happened by its dual code. It's also an MDS code, and if we apply the construction we saw before, we have obtained here two new maximal quantum codes. Okay, according to Marcus Grass table, these codes are new ones over F2. And again, using F2, again in a group algebra, here taking the cyclic group of 33 elements, its element, taking this element here, also we have it's easy to check this idempotent here, again fixed by element, by the evolution, and the code generated by this element and its dual is just some code with codes that have these parameters, and again, according to Marx Grass table, we obtain two new maximal entanglement assistant quantum codes. Okay, of course, since the element is fixed by the classical evolution, we have codes that are LCD codes. Okay. F3, the field with three elements. Here we have two possibilities: the group algebra, of course, and taking lambda equals -1. In this case, it's just 2. Here we have to be careful because in this case, when we compute g bar to 11, we have just it's equals 2. So this element is another important element fixed by the evolution. Here, the inverse of this any element here, g bar -1, is just gamma t -1 We can replace this, the inverse of the element g bar is just g -1 bar
times this unit.
Sorry, Samir, that 1 minute.
1 minute? All right. This code, the code generated by this element is a new maximal one, but the code generated by the dual code is not a new one, it's already known. And here you have another example in the twisted group algebra over F3, a cyclic group of 10 elements. Again, we can construct, but again, we can construct new maximal codes over F3. Just to finish, we have another different construction. It's called CSS construction. We have here, we have to have here some orthogonality relations, but we can explore these conditions using the involution. And if we have an idempotent, if we can put E times the involution, applying this element, and if this product is equal 0, we can prove this, the code is containing its dual. We can obtain another quantum codes with this condition. Let me present show you just this element, this example, and we have here that the length it has to be odd. So add one more. Thank you for it. Questions? Sorry. Questions?
I'm just curious that you mentioned that you are studying some cocycles of over D, right? Is that cocycle related with group homology? Or in what context you mentioned the cocycles?
Yeah, if you know something about homological algebra, you have to use here. But as we are using just some known results, we are working with some with cyclic groups, and for cyclic groups over fields and commutative rings, we have a complete characterization of this cocycle. You know, it has to be defined in this way. Maybe one of I plus k divided n the right side. For cyclic groups over commutative rings, all two cocycles can be obtained in this way. Okay? If we replace the group by, for example, a billion group, you have to be very careful with this two cocycles. Instead, we have the notion of cohomologous, and when the two cocycles are cohomologous, we have just the same ring, basically.
Thank you.
Okay, any other questions? So let's end again. So our last speaker is Hyutaro Matsumoto, and the title of this talk is Quantum are Delta Locally Recoverable Codes.
Thanks, Mr. Chairman. This is a joint work with Carlos Carrillo, Fernando Fernando, and Ellen Martin Class at UJI, Spain. And today, I would like to talk about erasures and erasures and local recovery. And an erasure means an error with whose position is known. And in the standard erasure collection, decoder uses all unerased symbols to recover erased symbols. On the other hand, local recovery uses as few unerased symbols as possible to recover erased symbols. And classical, which means messages and code words belonging to the vector space of a finite field, classical local recovery was motivated by distributed storage systems where each symbol of a code word is stored in a separate storage node. Our study considers quantum local recovery, in which messages and code words are quantum information, which are column vectors in a complex linear space of dimension Q. And in this talk, quantum local recovery will be reduced to the classical one by showing a novel equivalence between quantum and classical local recovery programs. Okay? And firstly, let us define IJ locally recoverable code. And in this talk, capital I always denotes the set of erasures, and J denotes recovery set. And classical linear code is said to be IJ locally recoverable if erased symbols in capital I of any code word can be recovered from symbols only in J, not in I. And the study of classical local recovery was initiated by these researchers in 2012. And informally speaking, a quantum error correcting code is said to be IJ locally recoverable if erased symbols in I of any code word can be recovered by unitary operators and quantum measurements acting only on the index set J. And the precise definition can be found in our ePrint. And the study of quantum local recovery was initiated by Dorwitz and Gursuami 2 years ago, with the special case of one erasure. And here, we consider general case of multiple erasures, which is new in our study. And we explain relation between quantum error correction and classical linear codes, which was also reviewed by Professor Gravel in this morning. And here, each quantum symbol in quantum message and code words is assumed to be vector in complex linear space. And quantum symbol is called a qubit. And a quantum error correcting code encoding k qubit message into n qubit code word is denoted by parameter nkq. And for two vectors x and y, we consider Hermitian inner product defined by this right hand side. And orthogonality in this talk is always considered in this inner product unless otherwise stated. And suppose that we have a linear code C over Fq squared, which contains its dual. Then this classical linear code defines quantum error correcting code with this parameter. So this is one description of quantum error correcting code by classical linear code. Okay? Then okay, this is our main result. Suppose that we have a classical linear code C containing its dual. And in addition, assume that the number of erasures is less than the minimum Hamming distance of C part. Then we have shown that C is ij locally recoverable in the classical sense, if and only if it is in the quantum sense. Okay? And a proof follows from the next page. And here, in this talk, we consider Hermitian inner product. And we can also obtain similar equivalence in Euclidean inner product. And we can obtain equivalence in with the CSS construction. But I will not talk about this today. Okay? Firstly, we consider classical erasure collection. And here, recovering set J consists of all indices. Okay? And the erasure set I is correctable if this condition is met. Here, Fq squared to the I is the set of vectors whose components are zero outside the index set capital R. So the left-hand side is just the shortened code to the index set capital R. And the proof is very, very simple. Consider rows of parity check matrix denoted by H1 to Hn minus k, and vector E is the erasure, and F is the single map defined by Euclidean inner product. Then the job of the decoder is to solve this system of linear equations. That is, erasure vector must belong to this set, and syndrome of this erasure must be equal to that of received one. Okay? And this system of linear equations should have unique solution. And this, how to say, condition is equivalent to F syndrome mapping F is injected on this set. And this is equivalent to equation 1 because kernel of this syndrome mapping is just the linear code C itself. So this is very, very simple. And in the next page, this, okay, equation 1, the linear code C is replaced by its punctured code in order to consider local recovery. Okay? In this page, we consider general local recovery. Here, J is any subset of indices containing erasure set capital R. And here we consider puncturing map Pj onto the index set J. And the Pj of C is the punctured code onto the index set J. Then the linear code C is ij locally recoverable in the classical sense if and only if this punctured code can correct erasures at I, and this is equivalent to previous equation 1 is code with punctured code, which is this. Okay? And in the next several pages, we will show that this is also a necessary and sufficient condition for quantum ij local recoverability if under the additional assumption that the number of erasures is less than the minimum Hamming distance of C bar. Okay? Here, we talk about some quantum error correction. In order, we review some details about quantum error correction. Suppose that we have a linear code C defining quantum code. Then, here H1 to Hn minus k is the basis of C part. Then, these basis vectors defines quantum measurements by the decoder for C. Then, measurement of a received quantum state gives syndrome, which is a finite field vector, as outcome of quantum measurement. And measurement by a decoder projects a quantum error, which is any unitary matrix, to a unitary matrix in a finite set of size q to 2 times 10, which can be then described by a vector E belonging to this finite field vector space. And in the quantum decoding, by a use of notation, we reuse a symbol F as a collection of inner product between H and error vector E. Okay? So Fe is a syndrome map defined by Hamisha inner product. And this is some unique feature in quantum error correction. Suppose that we have two error vectors in your V2. Then, even if they are different vectors, they have the same effect on every quantum code word if and only if two vectors are equivalent modulo CPAP. Okay? So, in the quantum error correction, the problem of determining error from its syndrome S is to solve a system of linear equations such that syndrome of E is equal to vector S modulo CPAP. Okay? So modulo CPAP is only difference in quantum error correction. Okay? And here, let us derive erasure correction condition in quantum setting. Okay? Here, C again defines some quantum code. And J consists of every indices. So we are just considering standard erasure correction in quantum setting. Then erasure in capital I is correctable if and only if this condition holds. And simple as the proof is almost the same as the classical case. Consider vectors of CPAP H1 to Hn minus k. And E is error vector. And F is the syndrome mapping defined by Hamisha inner product. Then the task of decoder is to solve a system of linear equations. Okay, that is almost the same as classical case. Okay, and this must have a unique solution modulo CPAP in order for erasure correction to be successful. And here, modulo CPAP is an additional condition in quantum setting. And this unique solution condition is equivalent to a kernel of F restricted to this okay, space is contained in CPAP. And here, this set is equal to C intersection Fq to the I. That is the shortened code of C onto the index set capital I. Okay? Then, because kernel of F is equal to C, which contains CPAP, this condition is equivalent to equation 3. So proof is again very simple. And in the next page, C in equation 3 is replaced by its punctured code in order to consider local recovery. Okay? Again, Pj of C denotes a punctured code of C onto the index set J. Then, here we consider Ij local recovery, okay, in the quantum setting. And C is Ij local recovery in the quantum sense if and only if punctured code Pj of C can correct erasures at I if and only if equation 3 in the previous page hold with Pj of C if and only this one. Okay? And we have identity that the dual of punctured code of C is equal to shortened code of the dual of C. Okay? So equation 4 is equivalent to this one. Okay? Here, the left-hand side is equal to the classical condition, but the right-hand side is somewhat different. Okay? And okay, so up to now we have shown that equation 5 is quantum Ij locally recoverable condition. Okay, And equation 2 was classical ij locally recoverable condition. And let us introduce additional assumption that the number of erasures is less than the minimum Hamming distance of C bar. Then the right-hand side cannot contain non-zero vector. Therefore, right-hand side is equal to zero space. So this additional assumption makes condition 5 equivalent to the classical ij local recoverable condition. So our claimed equivalence was dropped. Okay? And I would like to talk about this additional condition. When we consider collection of classical erasures at I, we usually assume that the number of erasures is less than Hamming distance of C. Otherwise, erasures at I may not be collectable. And in quantum setting, we are assuming C containing C bar. So this condition implies the number of erasures is less than the minimum Hamming distance of C bar. So this our assumption of classical quantum equivalence is almost always true. So by using this equivalence, we can translate many research results in classical local recovery to quantum local recovery with no effort. And I will show some examples. Okay? By translating classical definition, we can consider R delta locality in quantum setting. A quantum error correcting code said to have locality R and delta if for each index. Okay, so I skip this definition. Okay, and when we consider R delta locality, linear code C with Hamming distance larger than or equal to delta is considered. Along with this additional condition, C containing C bar, which is required to define quantum error correcting code, we have this fact. Linear code C has classical locality R and delta if and only if it has a quantum locality R and delta. And one can also derive many other results in quantum local recovery from this corresponding classical results, which are reported in our equation. So this is the end of our result, but I would like to talk about some open problems. Okay, this is a recent trend in quantum information processing. This is a title of some paper, and the point is that erasure correction is a hot topic in quantum computers. And when quantum computers uses qubit, binary qubits, which means the quantum symbol size q is equal to 2. Okay, so this is the point of this page. And on the other hand, since classical local recovery is intended for use in distributed storage systems, the code alphabet Fq can be arbitrarily large as each code word symbol is stored in separate storage nodes. So we can assume any size of Fq. Okay? So studies of classical local recovery usually, but not always, assume a large finite field. In contrast to this, in application of quantum local recovery to the quantum fault tolerant computation, we must consider Q to be 2. So Q squared is 4. So, but local recovery over small finite fields seems vastly unexplored in my knowledge. So, awaiting your investigation. Okay. Thank you very much for your listening. And these slides are available from my web page, or you can also send email to request this. Okay. Thank you very much for your attention.
So questions? Have a few minutes for questions. No, so let's thank again the speaker. So that concludes our section. And so presentations and all for attending. And actually, I have just one announcement about the cocktail. So if you want